All right. Welcome everybody to the community meeting. My name is Samhita. I'm with the Union AI team and I'm your host today. So do we have any new members who are joining the Flyte community meeting for the first time? If you're comfortable unmuting and introducing yourself, please feel free to do so. All right. You can also add your name to the attendees list. Let me share the link in the chat. Yeah, cool. And this meeting is being recorded and the recording will be posted on the Flyte YouTube channel. So the first item on the agenda today is news from the ecosystem. I'll quickly go through the topics that we think are worth knowing about. If you have any topic that you want to talk about, please feel free to add it to the agenda. So first comes LLM. Yeah, it's claiming itself to be an easy, fast, and cheap LLM serving with paged attention. It has been developed at UC Berkeley and deployed at Chatbot Arena and Recogni demo for the past 2 months. You can try it out with a single command. You can just pip install VLLM, load the appropriate model, and generate predictions. And the performance of VLLM is better than the Hugging Face transformers and Hugging Face text generation interface. So VLLM achieves up to 24x higher throughput compared to HF and up to 3.5x higher throughput than TGI. And the secret sauce behind VLLM is paged attention. So paged attention is an attention algorithm inspired by the classic idea of virtual memory and paging in operating systems. Give this blog post a read if this sounds like an interesting idea or if this is something you want to implement. And next, give me a second. Right. Andromeda cluster. So Nat Friedman and Daniel Gross have set up a cluster for startups and it's called the Andromeda cluster. All of these are like the technical specifications of the cluster they provide. It provides up to 10 exaflops of computing power. This is like next level support for startups. And then Gorilla. So Gorilla is an API store for LLMs. It enables LLMs to use tools by invoking APIs. Given a natural language query, Gorilla comes up with the semantically and syntactically correct API to invoke. So it allows you to use LLMs to invoke about 1600 plus API calls accurately while reducing hallucination. It is trained on 3 massive machine learning hub datasets, namely Torch Hub, TensorFlow Hub, and Hugging Face. And it's a fine-tuned llama-based model, and the creators claim that it surpasses the performance of GPT-4 on writing API calls. And next, GPT Engineer. It is made to be easy to adapt, extend, and make your agent learn how you want your code to look. So it generates an entire code base based on a prompt. This repository is all prompt engineering, and it proves how powerful prompt engineering can be. And yeah, David, do you want to talk about the other 2 items?
Yeah, could you click the link for the first one, please?
Sure.
Yeah, I thought this one was interesting because it was a survey on a number of the companies in the Sequoia network, which is an interesting network. And yeah, kind of 90% or more of them are using LLMs and a certain extent to different applications. But what's interesting for me first is that the only consensus is that there's no consensus on what will the end stack for LLMs will look like. Yeah, the majority of these folks are using foundational models, OpenAI GPT or Anthropic, but there's also a growing interest on 2 things. First, orchestration and development frameworks, which is interesting, and also open source. Well, it's not easy to build custom LLMs from scratch using open source. a growing number of these companies is trying to do it. And also one of the main drawbacks or the main issues that blocks them from moving to full-fledged production is security and privacy, which is, as we have shared, is very early days. So yeah, that was interesting. I don't know if there's any comment around this. No. Right, and the next one was, yeah, well, news from the ecosystem again, interesting move from Databricks acquiring Mosaic ML. They are well known for some of their foundational models, and kind of for me is the idea, part of the space race or the competition right now on LLMs is mostly on where to run this stuff. It's not where, if we need it or if we need to train them or whatever, where to run stuff that will make for the most efficient kind of infrastructure option. So it's again an infrastructure problem. So yeah, that was interesting to see. All right.
Thanks, David. Yeah.
Thanks.
And next, Flyte 1.7 release. So this was recently released. It features Flyte agents, revamped Kubeflow plugins, and numerous bug fixes and enhancements. So Flyte agents act as long-running services, stateless services. It reduces overhead and provides scalability benefits. Since the agent service can easily scale up or down based on workload demands. With Flyte 1.7, you should be able to write backend plugins in Python and also test them locally without the need to run the entire Flyte cluster, which I believe enhances the developer experience like a whole lot. And I hope we'll have a demo in the near future. So stay tuned for that. And thanks to all the contributors who made this release possible. Yeah, thank you. And next up is a demonstration of how to fine-tune LLMs with declarative ML orchestration. Niels, over to you.
Awesome, thanks, Amita. Yeah, hi everyone. My name is Niels. I do machine learning stuff at Union AI. And today I'll go through hopefully about 20 minute presentation and demo of fine-tuning LLMs using Flyte. I hope to spend maybe 5 minutes motivating why I do it in the first place, another 5 minutes going through a few techniques, and then the last 10 minutes kind of showing you Flyte code, Flyte UI, show you a few things going on there. So also as a caveat, there's a much longer presentation that we did at the Toronto Machine Learning Society workshops. This is a much condensed version of this, given the time constraint. So I'm going to breeze through a lot of these slides. We'll share this also, and it will share the larger presentation as well for people who want to dive in deeper. So quick motivation. Up over to the slideshow. Yeah, very toy schematic of the LLM. You give it an input, prompt, produces an output. Prompt engineering is the regime of you changing the prompts and working with the same model in order to get some desired output. There's kind of an in-between of prompt tuning. There's a lot of stuff that this field is moving very quickly, so terms are changing and evolving and things like that. But prompt tuning is the idea of having like a fixed suite of K prompts for a particular set of tasks, and you modify, you update just the input embedding layer of the LLM, thereby changing the weights, thereby changing the representations to optimize against some kind of output. On the other end of the spectrum is fine-tuning, where you have some data set, which is not pictured here, but you update the weights of the model directly, or to like bias it towards some distribution. Maybe you have some legal documents or some internal documents that you want to update your models so that the probability distribution changes towards those that token distribution. I'm not going to go through the pros and cons of each of these. They are essentially the inverse. There are a lot of inverses here. For example, with prompt engineering, you tend to have, you're interacting with it as an API generally, so you don't have to worry about machine learning per se. And then on the fine-tuning side, while you do have access to the weights and updating them, it is a significant, technical hardware, software challenge to like get these things to work properly. And then here's kind of like a tongue-in-cheek sort of flowchart diagram. Essentially, generally speaking, if you care about building an application on top of these, like prompt engineering is generally the way to go. And you should try really hard to like get the thing to work. But if you can't, then yeah, you go down into this area of needing like machine learning knowledge and skills to fine-tune these models. And a lot of this is data set cleaning and data set curation. Some prompt engineering resources. This is not the topic of this particular presentation, but folks can dive into these. At the high level, it's like to just write clear instructions. So now I'm going to go into like a bunch of techniques. And actually, I probably am going to skip a bunch of these slides because a lot of them are kind of intro to transformers and NLP kind of stuff. So the one I'll stick to, which is the topic of the Flyte code that I'll show you, is two types of fine-tuning. The first one is continued pre-training, which is just pre-training, but maybe instead of all the internet or Wikipedia and all scientific papers, you're like training it to predict the next token of some, proprietary data or something like that. Supervised fine-tuning is kind of like people distinguish this from pre-training by having a little more structure to the data. So instead of just a pile of tokens, you have like a prompt response type data set. And typically, unlike pre-training, you don't need the data quality to be super high. In SFT, supervised fine-tuning, you do want that, to be of high quality. I'm gonna skip through the transformers intro. I'm gonna jump straight to kind of like thinking about how much memory a model needs. Well, how much memory your hardware you want to have when you're training a model. So in the blue, you have like the parameters, in this case of the neural net, and the activations you'll need for those parameters. Generally speaking, let's say you're in floating point 32. To do updates on those parameters, you need to hold the gradients of those parameters. And assuming that you're using some stateful optimizer like Atom, you're going to also need momentum variance. So these are two additional things you'd need. So essentially, if you have 100 parameters, you'll need about 2,000 bytes of memory. You scale that up to think about how much you would need for a larger model. One thing you can do to increase the throughput of your model, during training, is you can use floating point 16. This is typically what you would see as mixed precision training. You typically want to represent your optimizer states in float 32 because of numerical stability reasons, but you can represent parameters, activations, gradients with floating point 16. There are a lot of different training setups, so this is just one of them. There are a lot of tricks that people have done historically to train models faster, right? So there's data parallelism, various optimizer breakthroughs and schedulers for learning rate, for faster convergence. The first technique I'll go through, which maps onto this deep speed package by Microsoft that I'll show you in Flyte code in a sec, is zero redundancy optimization, which is kind of it's a data parallelism technique that kind of takes inspiration from model parallelism as well. But at a high level, you shard the various states, right? So parameters, activations, gradients, optimizer states, and you have like n GPUs, and you shard them across those n GPUs. And there's a very like complicated pipeline for layer by layer. You kind of do the forward pass and the backward pass through the network. And there's a whole like communication protocol of like, okay, sharing the weights temporarily across those n GPUs for that first layer, doing the forward pass, saving that state somewhere, and then deleting all of the temporary weights, and then like going through layer by layer that way. So in pseudocode, essentially you do these various operations. So for each layer in your network, you do this all gather, you like distribute all the weights across all the GPUs, do the forward pass for that one layer, discard the weights, and then keep going, and then essentially do the same thing on the backward passes. So this, at the stage 3, so-called stage 3 zero parallelism, you essentially get memory reduction linear with the number of GPUs you're working with. I'll go through these real quick. 8-bit quantization, essentially you're representing floating points in lower precision, perhaps in integer representations. There are a lot of problems with this in terms of straining stability and the optimizer stability. At a high level, there are like a lot of tricks you can do to like get 8-bit quantization for both inference and training to work really well. This is all work done by Tim Detmers and a lot of people. So yeah, there's a lot of resources to dig through here. The punchline though is, with these bag of tricks, you can reduce the memory requirements by a whole lot and keep the same like performance for your models. The last technique is low rank adaptation, or LoRa. And the intuition here is that when you do updates of your model, right, you have some model weights W, you have some model updates delta W, and to do that update, you do, W prime is W plus the updates, right? Fairly straightforward. And to do the forward pass with the updated weights is, W prime X to get the new predictions. The intuition of LoRa is you can keep those things, separate, and mathematically you get the same thing. So you do WX plus delta WX, it's the same mathematically. So what if you can decompose the delta W weights into a smaller set of weights? And so this is the whole point of LoRa, where as you can see in the diagram, you freeze the weights here, so you don't have to keep any gradients or optimizer states for the frozen weights. And the weights that you do update can be orders of magnitude smaller. So you have a matrix A and another matrix B. And if you do the matrix multiply of those, if they're the right dimensionality, you can recover your delta W weight dimensionality. Which is basically this. And you multiply that by X, and then you effectively get the same thing. The thing is that the capacity of these two weights is much lower. So the theory is that for pre-training, you want to update all the weights, but for fine-tuning, you're like training on a much smaller kind of like set of concepts that your weights have to learn. So that's the hypothesis there, which is why, justifying why you can use much smaller weights and get pretty good performance on certain tasks. Okay, there are a bunch of notebook sidebars here that kind of implement LoRa and 8-bit quantization, toy examples of it. So I'll point you to these slides later. And okay, let's jump into fine-tuning LLMs with Flyte. So all of this code is open source. I'll point you to the repos later, but there are essentially two workflows that are featured in this repo. One is for continued pre-training. So essentially grabs Wikipedia data, like a subset of it, and then with deep speed, which is the zero redundancy optimization I showed you earlier, you can train a 3 billion parameter model on a single T4. And the pipeline will essentially fine-tune it, do 8-bit quantization, and then publish both versions to Hugging Face Hub. For model evaluation, this could be done by Flyte, but that's ongoing work. For now, I have like these two Google Colab notebooks for interactive inference, just using the notebook to generate text and evaluating the model. This supervised fine-tuning workflow is something that Samita has been working on for Slack data. So that, a little teaser on that work. But for now, we're just using the Alpaca data set to fine-tune an even larger model with LoRa. So this is the technique where you use lower capacity weights and swap. You freeze the main model and use lower capacity weights on that. So without further ado, I will show you the code. So here's the LLM fine-tuning repo. This is available on GitHub over here, Union AI OSS, LLM fine-tuning. And there's a lot of helper functions here, but the main crux of the code is over here, the Flyte code, that is. So you have this workflow that essentially does what I pointed out in the diagram. And the main thing of interest here is the training task. We're doing a couple of things here with the whole, declarative ML infrastructure piece. Besides requesting resources for the GPUs, we're also using the PyTorch Elastic distributed training framework. I'm debugging some issues here for specifying more nodes, but for now I'm using just one node. That would be one instance in AWS. The additional thing that needs to happen here is I need to provide a custom pod template that mounts a shared memory volume, and this is important for deep speed. That uses offloading, CPU offloading for weights whenever it's not actually using the GPU. So this is something that we needed to add to this task definition in order to get the deep speed plugin in the Hugging Face Transformers library to get to work. A few other things, secret requests for the weights and biases API key. You'll see that in a second. And then there's a bunch of code, training code down here. So you can look at that at your own time. But just to give you a sense of how this works, I'm using PyFlyte run, pointing to a Union AI hosted Flyte cluster, using a pre-built image here, and I'm passing a bunch of configuration files. And these you can see over here, using this Red Pajama Insight base model, 3 billion parameter base model, using the simple Wikipedia dataset subset. And then for my deep speed configuration, there's a bunch of it here. There are a lot of options. For the optimizer, the precision you want to use, and then a few others here for what kind of zero optimization you want to use. So hopping over to the Flyte UI, I've cheated here because all of these steps are cached. I do have a thing that's running right now. So this is hooked up to weights and biases. So this is just giving you a sense of how you can hook these things up together to get access to your training metrics. A few things to point out here. Besides the regular kind of Flyte stuff with the graph and timeline view, this is actually a cached workflow. So if we go back to the original source execution, you can get a sense of, there was a bug here, so I fixed it and then rerun it. So that's all the nice Flyte stuff. In the timeline view, just to demo like the extra metadata you get here. So you not only get a sense of like, okay, it makes sense that the training job took the longest, but it took about 6 hours in user code to run the training job. And yeah, that's it for the demo. There's a lot of more stuff to show. Perhaps I'll make a video that's a little longer that goes through this entire pipeline. But this is the LLM inference notebook. We're basically loading the model that we published on Hugging Face Hub to generate some text about Alan Turing. And then this is a notebook for evaluating the language model against a evaluation harness that's maintained by Luther AI. So this evaluation is ongoing, but this is something we can add into a Flyte task, produce a Flyte deck and all that nice stuff. The last thing I'll show is just to prove to you, this is on the actual Hugging Face, this Save to Hugging Face Hub task creates the string for where this is published. So you get access to all the model artifacts. So this would be the model artifact, and the tokenizer and stuff like that. And you can use the inference endpoints here, hosted by Hugging Face. And yeah, with that, I'll pass it back. Thank you.
Thanks, Niels. So Ketan has a question for you. Is it possible for you to show the utilization?
Yeah, I strictly had my open source hat on, but sure, let me do that. So just to be clear, this is a Union Cloud feature next to your execution attempt, the little button that shows up for viewing the utilization. And this gives you a sense of GPU utilization. I'm, pretty much at capacity here. This also shows you CPU and memory quotas and utilization, GPU memory utilization. So
you could have loaded a much larger model, right? And this.
No, so actually, yeah, we should take that offline, but effectively, yeah, no. Yeah. Cool. Awesome. Thanks, everyone.
Thanks, Niels. That was amazing. So anybody has any questions or feedback? All right, if there are no questions, joining us next is Fabio Gräetz, Senior Software Engineer at Recogni and a dedicated contributor and advocate of Flyte. Fabio will share insights on how Recogni has been leveraging Flyte. Fabio, the floor is all yours.
Yeah, let me check if I can share my screen. Can you hear me?
Yeah.
Okay, I have many screens open. I need to find the right one. Where is it? I'm struggling to find the right browser window. Ah, okay, because I have another tab open that was shown. So, give me 1 second. Right, okay, perfect. Now I have it. Can you see my presentation in the full screen mode?
Yeah.
Cool. Okay. Yeah, I'll briefly introduce myself, and then I'll also briefly introduce the company that I work for called Recogni. I'll then talk about why we use Flyte, why we love using Flyte, and I'll highlight 3 key features that that we use very, very often, and that just make our lives a lot better. So I'm Fabio. I'm, as Samhita introduced me, senior software engineer at Recogni. It's a member of the technical steering committee of Flyte. My background is in theoretical astrophysics. And before joining Recogni, I built up the MLOps team at a company called Aeronautics Momentum, where I also introduced Flyte. I'm based in Berlin, Germany. So Recogni. At Recogni, we develop neural network inference systems for the automotive driving industry or autonomous mobility applications. To the best of my knowledge, we have really unmatched performance amongst all of those automotive inference processing systems. For example, if I quote an MLPerf benchmark for single shot detection, like large object detection on 1200 times 2200 pixel inputs, we can run them on our systems at roughly 300 frames per second, and that at a very low power consumption of somewhere below 25 watts. So yeah, that is really it's really fast, really low energy, also very low latency. To make that happen, we have a patented processing system for neural networks that uses a logarithmic number system that allows us to greatly reduce the power consumption for the computations of neural networks. We are based in San Jose, in Silicon Valley, in California, and in Munich, in Germany. If you're interested about us, check out our website. I linked it here. I'll now talk a little bit about what our ML engineers do in their daily work. Also have a nice video here that shows it on the right. So we developed an in-house perception stack covering perception applications that are needed for autonomous mobility applications like classification, segmentation of driving scenes, 3D object detection, lane line detection in 3D, visual odometry, and others. And apart from developing this perception stack, our ML engineers also work on compressing and mathematically converting the models so that they can run on our hardware. And on the right here, you see 2 videos showing the same traffic scene. The top is the float neural network, and the bottom one is one that has been converted mathematically to run on our chip. I have another example here. The previous one was semantic segmentation. This one is 3D object detection. And on the right, you can see it in bird's eye view. Again, the top is a float model, regular float 32 model. The bottom one is one that has been compressed and converted for our chip. Probably it's very interrupted through the video because I guess when sharing the screen with Zoom, it's probably a bit interrupted. So to bring a float model onto our hardware, a few steps need to happen that we outlined here. So in the beginning, you have typically an O and an X graph of a float model and a calibration data set. And then we do post-training quantization with knowledge distillation using this on an X graph and this calibration data set, and out comes a model that has been converted mathematically converted for our hardware. And we have a compiler then that this converted model is the input for, and the compiler produces a so-called rex file, Recogni executable, and that one can then be uploaded to the hardware. So that's the process that our ML engineers typically do to bring float models to hardware. And that's also where Flyte helps us a lot for internal development. There are many steps here. Here it starts with the conversion of the float model, but even the float model needs to be produced in the first place, right? So we have workflows that automate everything from curating and pre-processing data sets, training float models, and then converting, compiling, and profiling them for our hardware. And since we're honing all aspects of that process, we need a platform for our ML engineers that allows them to self-serve their infrastructure, first of all, because we want to quickly try new approaches that might need very different infrastructure and hardware. And we want our ML engineers to do that in a self-serve manner. They might want to try a new architecture, need a different GPU type, different number of nodes. we want them to be able to do that on their own. And we want them to be able to automate everything so that our experiments are repeatable. We can change like small part and see what the outcome overall will be when the network runs on hardware. That's what we use Flyte for, basically automate everything. That's the motto. And that's why we love it. So I thought a bit about what I want to talk about, which features, and I will focus on three. The first one is distributed training and elastic training. The second one is pod templates, which in my opinion is one of the best features of the last half year probably. And then the last point that I'll highlight a bit is how we do continuous delivery for ML and how we use Flyte's Scrum schedule feature, which is a small feature, but I think it does great things for us. Okay. Talk a little bit about distributed training. So the data sets for autonomous driving applications are typically very large. And in order to speed up the training, we want to crunch through the data, not on a single node, on a single GPU, but actually on a larger number. And Flyte integrates very nicely with Kubeflow's training operator, which provides custom resource definitions for Kubernetes for distributed training with the different deep learning frameworks. We use PyTorch, so we use Kubeflow's PyTorch job. And to our engineers, it looks like this here. So in the task declarator, they just say task config equals to PyTorch. They say how many workers they want, how many GPUs each worker needs to have, and that's basically it. The rest is handled by the platform that we provide. But to the engineers, it's all abstracted away, and they don't need to know the details of how the different workers are started, how they communicate with each other. That's really cool because it makes it very easy for ML engineers to use distributed training without having to deal with the details of the underlying ops tooling. One of the business requirements that we have is that we can also perform distributed, in quotation marks, training on when executing workflows locally on a single node, a workstation that you might have under your desk. And for that, we upstream the plugin to Flyte that uses TorchRun, which you can use locally to do distributed training in a local worker group, but you can also do it on a cluster, obviously. I captured a small video that shows what this does. So if you replace the task config PyTorch here that you have in your task decorator with the newer plugin called Elastic, we replace PyTorch with Elastic here, and you provide the arguments that you would typically provide to TorchRun, then you can execute the workflow locally. That's something that you can't do with the PyTorch, with the existing PyTorch plugin. And then what happens is that something called Torch Distributed Elastic Launch, which is used to launch. Okay, I think I'll go a step back and explain what the cool thing is that's happening here. So when you use TorchRun or Elastic Training, you can have so-called local worker groups, which means that you run multiple processes on a single node, and then together with the worker groups on the other nodes, they form the entire world. That you can't do with the older version of Torch Distributed Training. So for example, let's say we want to train a model on 16 GPUs. You would, with vanilla Torch Distributed Training, start 16 containers. Each container gets one GPU, and then they communicate with each other. With TorchRun, you could say, for example, that you want to run only four nodes, 4 workers, but each worker gets 4 GPUs, and then within one node, one worker, or one pod in this case, we have 4 GPUs and run 4 sub-processes. So that the processes in that pod form a so-called local worker group. And the cool thing about that is that works also locally. So in the cluster, so in this scenario here, we want 4 workers and 4 processes per worker. So when you run that with PyFlyte in the cluster, you get 4 pods, and each pod runs 4 processes. So together it's 16. And when you replace the number of nodes with 1 here, then you can execute it locally. So nothing changes. You can out the wrong part of the video, but you can do Python workflow.py, and you get distributed training quotation marks locally. So you can use the same code, you just change one number, and you can go from running towards distributed training locally to running towards distributed in the cluster with more than one worker. So for us, that's really cool because it allows us to use the same workflow in a cluster where we have access to a large number of GPUs, but also on the workstation that we have under our desk where it's 2 or 4 maybe. And that flexibility is really cool. Yeah. Next topic. I'll talk about pod templates. So pod templates have been a feature in Flyte for a while. They were configured on the platform side. They could be configured on the entire platform level, on the project level, project and domain level, I think. I'm not sure if maybe even on the workflow level, but they were configured on the platform side. And since end of last year, beginning of this year, pod templates are exposed to the user as part of the task decorator, and that really gives a lot of power to users that I really like. And I'll show you 2 examples of what we do with that. So I think one concept that is very important in Flyte that I also really like is that it hides away the complexity of the underlying ops tooling from the users. And that's great because while Kubernetes is amazing, I don't think not everyone wants to use it, right? It's very verbose, and many ML engineers, they don't know how to work with it. And Flyte allows users to provision their infrastructure in a self-serve manner with Python. That makes it much easier to use. And here I have a task decorator where a user might want to request 1 GPU, and then Flyte turns this into a Kubernetes manifest for a pod. I need to move the videos, and it turns this description of a task here requesting 1 GPUs into a pod manifest, where in the resources section, 1 resource of type nvidia.com GPU is requested. And for us, that wasn't enough because our different perception applications are really optimized for different GPUs. And this didn't allow us to switch between, let's say, a T4 or a V100 or an A100 for different types of GPUs. So that was one of the key features that we needed while introducing Flyte at Recogni. And when pod templates got exposed to users by the task decorator, where we were able to do that. And I want to show you how here. So we wrote a small wrapper around Flyte's task called Recogni task, but it's really only a light wrapper. It provides an additional argument called GPU type. There's an enum that you can pass to it, different ones that are available in our cluster. And then in the Python code, but behind the scenes so that the user doesn't have to deal with it, we turn the GPU type, in this case V100, into a node selector that is understood by GKE, Google Kubernetes Engine. So the user says, hey, I want a GPU type V100, Python enum, and we, the platform engineers, then turn this into the pod template that has a node selector here. So with this feature, by exposing the pod templates to the users, we wrote a wrapper around Flyte's task that allows our users to switch between different GPU types, which was basically the only blocker why we couldn't roll it out to all teams at the same time, like when we first introduced it. We do 2 things, like 2 other things with Recogni task that I want to briefly talk about. We're just preventing that we run tasks on nodes that are more expensive than they would have to be. So what could happen, for example, is that somebody requests a node with 4 GPUs, the task finishes, task is still dangling, but then somebody else comes along and needs 1 GPU. Then the scheduler might say, hey, there's a 4 GPU node, perfect, let's just put the 1 GPU task on that one, preventing it from shutting down, and then we have 3 GPUs idling in the worst case if nobody else needs GPUs. And to prevent that, we gave additional labels and taints to our node pools with the GPU type. Again, GKE doesn't do that by default. They only give a label. We also created a toleration for the type and the count. And then in the background, in this Recogni task here, we set the required node selectors and tolerations for these taints that we created. So in this case, that means that when somebody starts a node with 4 V100 GPUs, somebody that requests 2 can't use them, so we prevent that resources are dangling and not being used. One other thing that we do with pod templates that is really cool is that we control rather in detail how the different workers in elastic training are being scheduled. For example, so there are two things that I want to show you here. So when a user does recognize task config equals to elastic, so that's this PyTorch distributed training, we want two things to happen. The first thing we want to happen is that we want all the workers to start only if all workers can start. What do I mean by that? In these days of large language models and generative AI, GPUs in the cloud are a scarce resource, especially when you want to have the ones that have more memory, like A100s, for example. And let's imagine, for example, a scenario where two of our engineers, they start a distributed training with A100s, and they both need 20 of them. So that's a total of 40. And if we're unlucky, GKE doesn't give us these 20 because they themselves are out of A100 GPUs because people are training their large language models. So what could happen is that both start their training, both want 20 A100 GPUs, and worst case, both of them get 10. That means that neither of them can start, but both of them started partially, and then we get timeout errors and torch distributed. Nothing happens. We still paid for GPU hours. And yeah, that's not great, right? Like engineers are waiting, or they started in the evening and expect to have results the next morning, but then they didn't because both tasks didn't get enough resources, while one of them might have, right? The other one wouldn't have, but at least one of them could have maybe. So we wanted to solve this problem in a way that a distributed training task only starts when all the pods can start. And what we did is that we installed the so-called co-scheduling plugin, which comes from a Kubernetes special interest group, into the cluster, and we configured the Kubeflow training operator to use that scheduler. In the background, it creates a so-called pod group, which ensures that the pods only start when all of them basically get a node. And then in this Recogni task here, it sets the scheduler name to the scheduler plugin scheduler, making sure that for distributed training tasks, this alternative gang scheduler is being used. Another thing that we want to do when scheduling distributed training workers is making sure that they're placed physically close to each other on nodes. So latency is higher, and also you can pay for network egress when the workers of distributed training get scheduled in different zones, and we need regional clusters because of because it makes it more likely that we can get GPUs, right? Than in a single zone, but we don't want the workers of distributed training to end up in different zones. And for example, then what Recogni task does, it creates a label in scheduling group, and it just puts some random string there. We have to create this at registration time, unfortunately. It'd be nicer to do this at runtime. And then we also put an affinity into the pod template that says, hey, all pods that have that match the label selector scheduling group and this random ID, we want to be in the same zone, basically. It's very verbose here, but that's what it ultimately does. All the workers of that distributed training, they will end up in the same zone. And you can also configure things like compact placement, that even within the same zone, they're placed near to each other on server racks that are very close to each other, if you really want to get the last bit of performance out of it. And it's really nice that we can do this now at the task level, because before the pod template was exposed only on the project level, we could have created a different project for these things, right? But what happens then to a task that isn't distributed training that we need for saving a model? It wouldn't work if this thing then also has this pod affinity here, right? So yeah, basically the TLDR of this, I think it's great that Flyte hides away the complexity of Kubernetes, because many people don't want to deal with it. But by exposing the pod template to the user, you give power users the ability to do what they want with raw manifests. And I think that gives us the best of both worlds. So that's really cool. Okay. The last topic, or the last cool feature that I want to highlight, is cron schedules. Might not sound like a big feature, but I think it's really cool what you can do with it. And our use case is that we want to detect regressions in ML performance very quickly. So we have, I didn't count, but quite a large number. But we have many ML engineers that work on a shared code base and develop their perception applications. And we want to prevent a scenario where one engineer makes a change and doesn't realize that it has some unwanted effect on somebody else's perception application. And then this gets discovered 3 months later, and then it's very hard to figure out which commit exactly introduced the regression, right? Because it will be very difficult to find that out then. So what we do is that, actually, I think I'll jump ahead to this slide here. So we register Flyte workflows in CI/CD. We do that anyways. Everything that is running on a feature or any workflow that is, let's say like this, any CI/CD pipeline running on a feature branch registers Flyte workflows in the Flyte development domain. Everything that runs on master builds, CI/CD builds, registers into the Flyte staging domain. And when we create GitHub releases, we register in the production domain. And I have this picture here from a really cool article from Google Cloud. Basically, the TLDR is it's great if you like treat your ML workflows like something that you release. So have your workflow code, check it into a source code repository, and then in CI/CD register the pipeline and then run the pipeline. So don't do it like don't treat it like a manually executed experiment that needs a human to be run. Treat it as something that's completely automated. You only do git commit, and then the rest is automated. That's the TLDR of this picture here. I think there's not enough time to go in more detail, but imagine it like this. Engineer checks in their workflow changes, make a PR, merge it, and then on the master build, we register this in the Flyte staging domain with the cron schedule, and then this gets executed on the schedule. So might look like this in Python code. The engineer would define their workflow here at the top, add workflow, and overwrote workflow name here, maybe not a good idea, and define some cron schedule, which is either for us it's a weekly or a nightly if there's a lot of development on that application. And that means that every night or every week we run the latest version of we train the latest version of a certain perception application. We log metrics and losses and statistics into 1DB, and then we also compare to the last run and to the best run, and then automatically alert on Slack if there's a regression. And that allows us to detect rather quickly when we introduce a change that either leads to a 5% F1 score drop, for example, or leads to memory consumption doubling or training time to triple or whatever. We'll notice these things right away. And then it's typically not a large number of commits that we need to check to find out which one it was. And by registering workflows in CI/CD and then having these cron schedules that we run regularly, I think it helps us a lot to improve certain metrics that we're interested in over time and not risk regressions there. And with these launch plans here, with the cron schedule, I think it's pretty easy to do that, which is very nice. Maybe one last word about this. What I'd like is that automatically always the last version gets run, so you don't need to worry about deactivating previous ones. You just register with PyFlyte register Python module that creates these lines of code here, and then the last version on master is the one that we execute. It's really convenient. Okay, yeah, I talked a bit about a company that I work for called Recogni. We develop crazy fast inference processing systems for autonomous mobility applications, and we develop perception tooling and conversion compilation tooling for bring networks onto our hardware. I talked a bit why we use Flyte for that, and then I highlighted three key features that we like a lot, which are distributed training and elastic training, pod templates, which really allow power users to do whatever they want with the Kubernetes pods, and lastly, cron schedules that allow us to detect regressions pretty early. And yeah, I want to thank you for listening to what we do. And if you have any questions, I'm happy to answer them.
That was a fantastic presentation, Fabio. It's great to see. And we love having you in the community. So thank you for being part of the community and
thank you.
Helping the product make it so much better every day.
So I would have a question that's slightly on a tangent. Martin from Black Shark. How did you convince your ML engineers to start working with it?
I think I was hired to solve a problem that was existing, right? And the first conversation that I had with the company that told me, hey, we have an orchestrator, but we were growing very fast and it's difficult to onboard people. We need something that scales better. And then when I joined, we looked at different tools that existed and made a list of requirements, what we need in order to make it work. And I had done such a comparison at the company that I worked at before. And back then we decided to use Flyte. And I knew that, like, I saw the list of requirements and knew that I could build a prototype that would tick all those boxes. And then I built a prototype for that. And we then compared it to another tool that one of the other ML engineers proposed. But in the end, there were a few boxes that we couldn't tick there. And yeah, I mean, when the platform users saw how it would look like, I think it was very, very easy to convince them. One feature that didn't exist back then was the ability to switch GPU types, and let users have control over that. And that was the blocker that we had in the beginning. Why it took, I think, like 4 or 5 months to bring all the applications that we now run on it over. But with this pod template feature, then we could do that. And then, yeah, that allowed us to switch everything over, basically.
Okay, cool. Thanks.
Martin, that was actually a very good question, because I think most community folks have this sort of questions. Like, how do I, in our community, we have 2 types of people: practitioners, which are the ML engineers, and the platform people. And many times we end up having that the platform folks like Flyte a lot, and they end up using it because of XYZ properties, and it fits and solves many other problems, right, that they have, like in your case, probably data as well as the ML inference time. And then the ML engineers are also part of the community. And so this exchange was extremely useful. And David, hopefully we can capture it and share these as a set of, like, do a quick prototype and share. And adding that different GPU selection, I think we have to do it.
There is an RFC incubator.
I know. Probably we should just accelerate through it. Accelerate the accelerator selector. So. Fabio, one comment I had was, you said the labels cannot be passed at runtime. They can.
They can be parsed at runtime, but we need to create, so in this affinity, we say, hey, all the pods, I want to be in the same zone with all the pods that have the same label key and value. And we need a value that will be different for a different, like, execution ID, right? And so we need something, we need a key value pair that will be different for different executions IDs, but that we know at registration time, because we need to write it into the pod template. So we need to know the value that is random during registration time. And that's why we have to generate one. For us, that's not a problem right now. Like, it would become a problem if we run the same workflow version a lot on different inputs, right? Because then they would all share the same affinity. So at that point, we can't do that anymore. But that doesn't happen currently for us, because we run these weeklies, but that's just one instance of the latest version. And then we have many different versions on feature branches, but there we register again, right? Because we do quick iterations. So for us, that's not a problem currently. We thought about doing it with a mutating admission webhook. There we could have just patched this into the pods at runtime. And I guess we'll do that if we run into the problem where we have a larger number of workflows that attract each other, even though we wouldn't want them to, right? And I guess we go to mutating admission webhooks. But until then, I think this is a pragmatic solution that does the trick.
Martin just commented that they have had GPU selection for tasks since September 2021. Martin, where is the upstream? Yeah, so for Fabio about that, though, I would love to understand, did you even try other schedulers? Like, I know people have talked about Unicorn now, and then there's another one. Volcano batch, which I think has fallen out of interest for a lot of reasons. There's another one in Kubernetes 6. So yeah, if you have tried any of those, let us know. We've also tried. We've not had very good experience with some of them. But yeah,
I compared. So for the scanning scheduling feature that we built a while back, we compared Volcano and scheduling plugins from Kubernetes 6, and both of them would have worked for me. And the easier one to get to work was scheduling plugins. So I picked that one.
Yeah.
So Volcano, I think, has more features, but I didn't need these features, and it came with a lot more overhead. Also, like the scheduling plugins, you have to build you have to package the Helm chart yourself. So it's, or you would have to check out the repository. So it's not super convenient to do, but you can get it to work, and it hasn't posed any problems since.
Any more questions? All right. I personally loved your presentation, Fabio. Thanks for sharing your journey with us today. And yeah, that's all for today. The next community sync is on July 11th. If you'd like to speak, please add your name to the table present at the top of the agenda document, or you can also just let us know. Thank you so much for your time and participation. See you all at the next community sync.
See you.
Thanks, everyone.
Thanks.